So if there are any questions during the class, please just type in the chat and I will try to respond accordingly. Okay, today we are going to cover this topic, calibration and noise. So basically, with regards to the class, if let's say you can join the class on Tuesday, then you are welcome to do so. So you don't have to join the class today. This is as backup for those who cannot make it on Tuesday. So we are going to have this class to make sure all of you have enough time to study the material. Today we're going to cover on calibration and noise. So this is the expected learning outcome by the end of the lesson. So number one, for you to be able to explain the principle of calibration. Number two, to list basic calibration parameters for analog, DC and AC meters. Number three, to calculate calibration parameters for potentiometers and volt box. So these are the two items that we are going to look into on how to calibrate today. And number four, to describe the sources of noise during the measurement and ways to minimize it. Okay, so A, B, and C are basically the same subtopic, and D is another subtopic. Okay, what is the definition of calibration? So basically, it's to check and adjust, if necessary, the response of a measuring instrument so that the output corresponds to the input throughout a specified range. Okay, that is the technical term. Basically, when we calibrate, we want to make sure that our measurement is correct. That's the essence of it. Okay, and then to range an instrument, range ni usually apply for analog instrument. We want to set what is the range for its operation, measurement operation, because we want to control the desired sensitivity. Okay, sensitivity is how fast it responds to the changes. Okay, the more sensitive, that means the more it changes as the input value changes. Okay, so to rearrange analog instruments can only be done through recalibration. And for digital instruments, they are usually separate, calibration and ranging. Now, most of our instruments are in digital form, but we still need to study analog because in the industry, there are still many instruments that is based on analog reading. Especially in power systems, electrical power, if you go to substations, many substations are 30 years, and during that time, many of the meters, they still use analog meters. So we need to understand the principle operation of meters, whether analog or digital, so that we have a better understanding on how and when to use it. Most of the calibration needs to be done either in the lab or you need to send it to accredited laboratories that you need to pay a certain amount for your calibration. But one of the simplest type of calibration that you can do directly is for time calibration. Now, if I open a website, so yeah, this is the attendance. Just now, I can only access the manufacturing students. So the list for BKG is not available yet. Okay, if I type here mst.sirim, you will see this interface. MST stands for Malaysian Standard Time. And this is the standard time for Malaysia. And it's stated here that is maintained by the National Meteorology Institute of Malaysia, NMIM, which is an institute under SIRIM. Okay, so this is the standard time that we can use to calibrate our clocks and watches. So here, if we check, it's already mentioned that the accuracy for this time is 0.1 second. Now, as a comparison, let me check with my computer time, whether it's the same or not. Okay, so my computer time shows a difference of about 3 seconds. And if I want to, I can calibrate this and I can set it so that it matches the Malaysian Standard Time. So you can also look at your clocks, watches, your mobile phones, and see whether the time is accurate or not. But after some time, let's say maybe 1 week or 2 weeks, depending on the accuracy of your internal mechanism for your clocks and watches, after 1 week and 2 weeks or 2 weeks, if you check again, there will maybe be some differences by a few seconds. Okay, higher quality watches, they will have a higher accuracy, higher precision, but lower quality watches, it tends to shift away from the actual value. So if you remember if you refer to the slides on error, static characteristic of measuring instrument, then it falls under the deviation or sensitivity to environment, to disturbance. Okay, these are examples of calibration you can do on your own. Coming back to the slide. So for calibrating analog instruments, we have a few definitions. So in the lab, usually we have a standard instrument. Standard instrument is the instrument that we use to calibrate other measuring instruments. Usually we can use digital instruments as the standard instrument because they are typically have higher accuracy and precision. So that's why we can use that digital instrument. And we can also check the performance of digital instruments with other digital instruments to verify whether it's good or not. Okay, this is the standard setup for analog DC voltmeter. So for this setup, we want to calibrate the meter here, and this is the standard meter we use as reference. So this is an analog voltmeter, this is a digital voltmeter. This is a regulated DC voltage source. So regulated means control. So you can set what is the exact voltage source that you want. And then we have a variable resistor to control the magnitude of current that is passing through from the voltage source. And we can use this basic circuit to calibrate our voltmeter by placing the voltmeter in parallel. Okay, and then we also have this resistor here. What is the purpose of this resistor? So the purpose of the resistor is so that we can compare the voltage across. So because of principle of parallel, the voltage across this meter, this resistor, and this meter should be the same voltage. So the reading should be the same. If the reading is not the same, then we can calibrate so that the voltmeter follows the standard reading. Okay, this is the setting for analog ammeter. So if voltmeter we put in parallel, for ammeter we put in series, the same principle. So we want to know what is the current flowing in the circuit. So using this principle, we can compare the performance. Okay, using Ohm's law. Okay, this is the setup. And we can also calibrate ohm meter. Using the accuracy of the instrument can be checked by measuring different values of standard resistance and noting the reading obtained. So for measuring the resistance, usually calibration only involves adjusting the 0 ohm knobs. Now we are talking about analog instruments. Okay, I'm sure you are well aware of this. You are direct entry students, so by right you are mostly from diploma background, I assume. So you must have experience using meters. I don't know whether you have experience using analog meters, but most probably you have. Just as a backup, I'll show you the figure of a meter. You can see it here. So this is an analog multimeter. So if I scroll down, you can see here the setting. We can measure either DC voltage, AC voltage, DC current, and also resistance. So now assume we are measuring resistance. So resistance is the blue color, the scale with the blue color. So it refers to the top scale here. So for the DC and AC, the starting point 0 is measured from the left hand side to the right. So the more magnitude, the higher the magnitude, then the needle will move towards the right. But for resistance is the opposite. When you set to resistance, then the needle will start here at 0 ohms. So the top scale here. Okay. After multiple usage, sometimes when you set to 0 or you set to resistance and then you short the two probes, the red and the black probes, you short it together, you connect the connector, then the needle will move towards 0. But sometimes it's not going to be directly 0. It's going to shift maybe a bit to the right, to the left, or a bit to the right. So you need to use this one here. It has a label of ADJ, that means adjustment. So you can adjust using this knob so that the needle points on top of the 0 scale. This is what is meant by the statement here. 0 ohm adjustment knob. So for the AC voltmeter and ammeter, the instruments can be calibrated using comparison methods, just like what I have shown just now. Okay, now we move to potentiometer. Okay, before we move towards potentiometer, we need to know a bit about loading effect. Okay, loading effect will always affect the measurement. Even when we have a high input impedance, a small loading effect still occurs. So one of the solution is to use a device called the potentiometer. And this device can be used because it does not involve any current flowing inside it when the circuit is being measured. So what is loading effect? A simple example is shown in the figure here. If you see here, this example is when you want to measure a current flowing in a circuit. So let's say the current has these resistors here or these elements here. So you want to measure the current. But actually, the ammeter itself also has resistance. So RM here is the abbreviation for the meter resistance. M stands for meter. And that resistance becomes part of the circuit. So now when we measure the current instead of just these two elements, now it will be affected by the element of the meter itself. So now the current becomes actually smaller than the actual current flowing if there is no meter. This is what we call as loading effect. Okay. So the formal definition is when the measurement instrument itself affect the value we are trying to measure. So how to solve? Can you propose any solution? What must be the characteristic of the meter? You cannot say that the meter will make sure the resistance is 0. It's impossible. There must be some form of resistance for the current to flow. Okay, so what is the solution? Maybe one of the solution is to try to minimize the resistance of the meter by using high quality conductors inside or high quality coils inside. Okay, of course there are some other methods, but one of the solution provided is the use of potentiometer. Okay, what is a potentiometer? So potentiometer is a device that can be used to measure voltage across an unknown element or unknown component by the principle of voltage divider. So it can measure the voltage between two terminals of a circuit with known characteristics. Kalau kita tahu dia punya sifat-sifat dia. So how does it do it? We measure the voltage by comparing it with a standard cell. Okay, nanti kita akan tengok dia punya schematic diagram. Measure the current by measuring the voltage drop produced. And then we can also measure power if the time is measured. Kalau sekali dengan potentiometer ni, we also measure the time. We can use the equation voltage and time to calculate the amount of power. Okay. So this is the setup or the diagram of a potentiometer. Now, what does a physical potentiometer look like? It looks like this. So your slide maybe not updated yet. The one I uploaded, I didn't include this picture. So I'll upload the latest one soon. Okay, so this is an example of our potentiometer. So you have a slider here that you can move along the line, and you have the terminals here at the bottom, or we can call it as the pin. Okay, so you can see the diagram here. So we have the yellow one is the input and the output. If we go back here, so the red dots is the position where we connect our voltage source, the input and the output. Okay, so these red dots here are equivalent to the yellow pins here. And then this pink pin here will depend on the position of the slider. So the slider, as you move it to the right or to the left, the resistance will change. And when the resistance will change, the voltage will change. So it will be reflected by this other pin here. So this is the schematic diagram of a potentiometer. Okay, so before I move on, let's see what are the application of potentiometer at present. Now, many potentiometers. Okay, hold on, I need to answer this. Hello. Tengah kelas. Okay, so coming back to this point, what is the current application? Now many application for the potentiometers has been replaced by digital equipment equivalent. But one of the field that still uses some form of potentiometer is in mixing consoles. When you want to control music, or when you want to manage PA system. So this is an example of a mixing console. So to control the volumes and all the variation of the types of sound, so we use the potentiometers at the bottom here. Okay, this is one practical example. When we want to control the volume or the audio. So now we want to learn on how to calibrate what we call as a slide wire potentiometer. So this is what we call, this is the definition of slide wire. So when we move it, we have a slide wire. So this is the circuit. If you look at the circuit diagram, you see that we have S here is a switch. So switch, you can move from operate to calibrate and so on. And then we also have a switch that connects the galvanometer to the slide wire. And the slide wire, we have a battery. The battery will supply the current that will flow inside the circuit. And the rheostat is basically a variable resistor we use to adjust the level of current that we want to flow, to allow to flow in the circuit. So we want to measure, let's say, a voltage of an unknown component. So we are going to place it here. And the step is given as follows. So let's say we want to determine E. So first we need to know E1. So to know E1, we need to calibrate first. So to calibrate, the first step, we put at position, the switch here, the arrow here, we put at position calibrate. And the standard cell is going to be used as the reference. Okay, then the next step is the switch S is put at operate position. So you turn the switch to operate position and the galvanometer key kept open. So you don't touch the galvanometer to the slide wire yet. Then we slowly slide the galvanometer key. So we are going to slide from point A up to the point where the galvanometer stops moving. So galvanometer is a device that detects, very sensitive device that can detect small amount of current. And we move the resistance until we reach a point where the galvanometer does not deflect anymore. So that means no current is flowing. So when no current is flowing, that means the voltage here is going to be equivalent to the voltage at that point between A to, let's say, point C as given in part 4. So we can move along until it reaches one point, let's say point C. If the galvanometer does not deflect at that point, then we can calculate using Ohm's law to find what is the voltage here. Okay. So let's look at an example of how to calibrate a slide wire potentiometer. So the length of the slide wire in this example is given as 200 centimeter. Overall resistance is 100 ohms and a 3 volt working battery. So internal resistance is neglected. We assume a standard cell reference voltage source of 1.019. This is the standard cell reference. And the sliding contact is set to 101.9. So you see there's something, some equivalence here between the voltage and the position. So calculate the working current, measurement range, and adjusting value of the rheostat. So how do you tackle this problem? So to determine the working current, we first determine what is the resistance at the point where the position for the standard cell is located. So the length when the standard cell is used is at 101.9 centimeter. The total length is 200 centimeter. So we can use this equation, the ratio of the length multiplied with the total resistance to get the resistance at this point, 101.9. And the value is given as 50.95 ohms. Now using Ohm's law, we can determine the working current by dividing the voltage with the resistance. So the voltage is given as 1.019. The resistance is 50.95. So we get the working current is 20 milliamps. Okay, now we need to know what is the measurement range. Again, we apply Ohm's law. The current is 20 milliamps. The resistance is the total resistance, 100 ohms. So you get the voltage that you can measure is 2 volts, the measurement range. So this is the limitation of a potentiometer in this context. It can only measure up to a range of 2 volts. So next, we need to determine what is the value for the rheostat. What is the value for the variable resistor to make sure that the current is at 20 milliamps. So we know from the circuit just now that from here, battery up to the same point back, this is a complete circuit. So the voltage from the battery is equal to the voltage drop at the rheostat plus the voltage drop at the slide wire. So voltage drop here is not considered because it's a parallel circuit. This circuit is going to be parallel to this circuit. And when we open it, we only consider when we open the point K here, we only consider this circuit here. From A, going to the battery, rheostat, going to this point, and coming back to A. So, we know that the voltage of the battery is equivalent to the voltage across the rheostat plus the voltage across the slide wire. So we modify the equation to find that the voltage of the rheostat must be 1 volt since the voltage of the slide wire is 2 volts. And again, we apply Ohm's law to determine the variable resistance value, which should be set to 50 ohms. So this is how we calibrate a slide wire potentiometer. Okay, now please try to do this. It's the same concept, but with different values. So now the length of this slide wire is 200 centimeter. And we also have a scale, 200 centimeter scale. Basically like a ruler. Macam satu pembaris. Kita letakkan along the slide wire. And the slide wire has a 1 millimeter scale division. So the scale is 1 millimeter scale. We can see up to 1 millimeter. And it is possible to read up to 1/5 of a division. So dia boleh baca up to 0.02 lah millimeter of the division 1 divided by 5 multiplied by 1 millimeter. So the standard cell is 1.018 and the sliding contact is set to 101.8 centimeter. Okay, so calculate the working current and measurement range and adjusting value of rheostat and instrument resolution. So remember the impedance or the resistance is 400 ohms. Okay. So how do you solve this? So I've already done the solution yesterday. So I'm just going to share with you the step. Alright. So referring to the circuit, the voltage for the battery is given as 3 volt. The resistance of the slide wire, this blue line here, is 400 ohms. The length is 200 centimeter. And the standard cell is given as 1.018 volts. So part A, to determine the working current, we find the ratio of the resistance at the point 101.8 centimeter. So we divide with the length, so the centimeter cancel, and we multiply with the total resistance, so we get a value of 203.6 ohms. Using Ohm's law, we divide the voltage from the standard cell with the resistance to get a value of 5 milliamps. So if you can imagine, the position of the switch at this point, it is at calibrate, not at operate. So the switch is positioned at calibrate. We get a value of 1.018 volts here. And we divide by 203.6 ohms, which is the resistance at point 101.8 centimeters, somewhere around here. So the position is there. So voltage divided by resistance, we get the current as 5 milliamps. Okay, now to ensure that the current is set to 5 milliamps, we need to determine the value of the rheostat. So the value of the rheostat, the resistance must be the total resistance minus the slide wire resistance. So the total resistance is the voltage from the battery divided by the total current. So you are going to get here 600. 3 volts divided by 5 milli, you get 600. Minus by 400, so you get 200 ohms. This will be the value of the resistance at the rheostat to make sure that the current is fixed at 5 milliamps. Because the battery source is fixed at 3 volts. Okay, so this is how you solve part B. And then for the measurement range, again we apply Ohm's law. So we have the current 5 milliamp, the total resistance 400 ohms. So multiply, we get 2 volts. And the resolution, so the resolution we have 2 divided by 200 multiply by 1 over 10, so you get 1 millivolt. So 1 over 10 here, why we have 1 over 10? Because 1 centimeter is equal to 10 millimeter, so we want to convert into millimeter reading. So that's why we have 1 over 10. What else? So because the reading accuracy is 1 over 5, so we multiply 1 over 5 with 1 millivolt to get that the resolution you can read up to 0.2 millivolt. So quite accurate. You can measure from 0 to 2 volts, and the range of accuracy or the resolution that you can read is up to 0.2. So that means the reading can be 0.2 millivolts, 0.4 millivolts, and so on up to 2 volts. That is the resolution based on the range. Okay. So 12:35. I'm not going to take any break because I want to finish within 1 hour. If you have any questions, please upload or please write down in the chat. If not, then I'll move on. Okay, tadi we talk about slide wire. Dia memanjang, slide wire. Now we talk about another type of potentiometer, which is called the single range dial potentiometer. So it has 2 dials as a variation of the slide wire potentiometer. The advantage of using a single range dial potentiometer is it does not require long or large size. We can decrease the physical size of the meter. It can shorten the time for you to take the measurement, and you can have better reading in terms of accuracy. So the concept is the same as the slide wire, only the arrangement of the wire is now in circular form, not in linear or straight form. So you see something shaped like this. So on the right hand side, this part here is actually a potentiometer without the second dial, only one potentiometer. So you commonly see these types of potentiometer for controlling audio or for controlling certain amount of resistance in your circuit. You see these types of potentiometer. Okay, and on the left hand side is a schematic diagram of a single range dial potentiometer. This one has 2 dials. One is the main dial and one is the slide. And we have also a circuit somewhat similar to the slide wire circuit with some differences. So we still have a battery and a rheostat. Okay, so this part here is the equivalent to the slide wire, the straight slide wire. And we also have the switches to operate. So ES is the standard cell we want to use as the calibration, and EX is the component that we want to measure the voltage. So again, we see that the switch we can change from cal is calibrate to operate. So let's see how it works. So the calibration method, we set the direction needle of the main dial and the slide wire dial to the standard voltage value. So let's say the standard cell is used is 1.019 volt. So first we set the direction needle of main dial to 10 stages. So if every stages represents 0.1 volt, usually in the questions we set something simple like this. And then number 2, setting the direction needle of slide wire to the divisions of 19 if it has 100 division. So the main dial has 10 stages and the second dial or the slide wire has 100 division. So we can use this concept here. We have 10 stages multiplied by 0.1 volt. So you get 1 volt here. And then 19 divisions, multiply by 0.1, divide by 100, so you get 0.019 volts. So this is how we calibrate. Okay, so the step is as follows. So first, the switch is connected to the calibrated point. So you see indicated by the red arrows here. So now we have a standard cell. So the standard cell 1.019 volt, we put it at ES. So we have the circuit here, connected here, passing through the dial, the battery, rheostat, and the connection point to the galvanometer and the protection resistor, and it goes back to form a complete circuit. So we adjust the position of the rheostat until there is no deflection on the galvanometer. We adjust the resistance until there is no current flowing in the circuit. After there is no movement of the galvanometer, we need to remove this protection resistor. Okay, so we have this line here where we short circuit the protection resistor. Now the purpose of protection resistor previously was to make sure that there is no excessive current flowing in the circuit when you do the calibration. Once you have made sure the galvanometer is set at 0, there is no current, then we need to remove this protection resistor and then adjust again to make sure there is no deflection. So there will be just some small adjustment, not here at the rheostat, some small adjustment to make sure that the galvanometer does not deflect. Okay, this is when you calibrate. Now when you want to measure the voltage, you want to put the component you want to measure at EX. So you change the switch to operate, and then the circuit passes through this component here. So the measured value of EX is recorded by adding the value read from the main dial and the slide wire dial. So what is the value here plus the value here? That is the reading. Okay, this is a simple example. So we have two dials potentiometer, consists of 20 stages of a main dial. Every stage is 10 ohms. So we have 20 stages, every stage is 10 ohms. And every stage is represented by 0.1 volt. And then we have a slide wire, resistance is 10 ohms with a division scale of 200. And the working battery is given as 6 volts. So again, we want to calculate the working current, measurement range, and adjusting value of rheostat. Step. First, we need to know what is the current based on the first stage or the main dial. So since each stage represents 0.1 volt and resistance value for each stage is 10 ohms, so we apply Ohm's law to get the total current flowing is 10 milliamps. Now we determine the total resistance. So the total resistance comes from the main dial and the slide wire. So if you go back to the slide, the total resistance comes from this line, this part here plus this part here connected to the circuit. So we need to add them together. So we have 10 ohms multiplied by 20 stages, so we get 200 ohms. And then for the second stage, for the slide wire, is given 10 ohms, division scale is 200. But even though the division scale is 200, the total resistance is 10 ohms. So 10 ohms multiplied by 20 stages, we get 200 ohms, plus 10 ohm from the slide wire division scale, so we get total resistance of 210 ohms. And then the measurement range, we multiply the current 10 milliamps with the total resistance, we get the voltage as 2.1 volt. And then to get the resistance for the rheostat, again, first we calculate the voltage drop. The voltage drop is equal to the voltage from the battery minus the voltage drop from the slide wire, from the single range dial wire. So we get 3.9 volts. Because we want to maintain the current at 10 milliamps, so we use this equation to set the rheostat resistance at 390 ohms. So this is how we calculate calibration for single range dial potentiometer. Okay, so of course if we can do practical, then it would be better. I try to check at the lab. I don't find any single range potentiometer yet. If I find, then maybe I can try to do a short video on how to do the calibration manually. I mean like physically. Kenapa kena darab 20? Okey, kita tengok soalan. Soalan kata there are 20 stages. Each stage, every stage has 10 ohms. So 10 ohms every stage. There are 20 stages, sebab itu 10 multiplied by 20. Kenapa dia 20 stage? Kalau kita tengok figure ni, dia bergantung kepada single range punya setup dekat sini. Ada berapa point yang dia boleh ubah setting dia pada main dial ni. Biasanya, dalam design untuk single range dial potentiometer ni, dia akan set main dial ni pada nombor gandaan 10. Biasanya sama ada 10 stage atau 20 stage. So, lagi banyak stage tu, maknanya lagi besarlah range yang you boleh measure. Okay, kalau dia ada 10 level saja, then 10 darab 10 you boleh measure 100 ohm. Tambah 110 ohm, so you bahagikan, ada limitation dia. Tapi lagi banyak stage, lagi besar range yang you boleh measure. So itu nak jawab soalan kenapa apa dia stage 20 tu. So stage tu rujuk pada, kalau gambar ajar ni rujuk pada titik hitam ni. Pergerakan dia. So bila you adjust, bila you tambah, you nampak garisan ni adalah resistant yang bentuk macam kelopak bunga ni. Dia sebenarnya adalah wire. So wire tu ada resistance. So kalau you switch dekat sini, okay, dia akan consider resistance pada line ni. Bila you switch kat sini, dia akan combine. Line sini campur dengan yang kat sini. Bila you switch sampai kat sini, dia akan combine semua resistance yang ada kat sini. Sebab itu resistance tu akan bertambah. Okay? So jawab soalan tak? Harapnya faham lah. Alright. Okay. Yang ketiga adalah vote box. Okay, vote box ni lebih mudah. It's simpler than potentiometer. So you want to measure the voltage. What is the common rule yang you belajar when you want to measure a voltage of an unknown component ataupun unknown part of the circuit? You punya instructor kata measure the voltage, but you don't know what is the range of the voltage. So what is the common practice? You must start with the lower range or higher range. Cuba type sikit, lower range or higher range. Kalau you tak tahu voltage dia berapa, yes, higher lah, common sense kan? Sebab bila you tak tahu berapa, you tak nak damage the equipment of the meter. So you start with the higher range. Bila you dapat bacaan dia terlalu kecil atau tak jelas, barulah you turunkan sehingga you dapat the voltage that you want. So thank you for your response, for your engagement with the lecture session. Okay, semua betul. So kita akan gunakan konsep voltage divider. So let's say we want to measure the voltage across these 2 points, positive and negative. So we are going to set higher resistance first. And then we're going to step down, lower, depending on the voltage level of what we want to measure. But if we want to design the vote box, we need to start with the lower value first, and then we slowly increase. So we need to start with R1, and then R2, and so on until we reach R5. So this one uses the concept of voltage divider. Okay, how we do it? So a vote box, we must set the resistance value to ensure that the output does not exceed the measurement range of the potentiometer. So we add, because the resistance all are positioned in series. So if we add them together, the resistance will increase. That means the amount of current that flow will decrease, and we can measure higher range of voltages. Okay. So let's look at the simple example here. So design a vote box with the ranges 5 volts, 10 volts, 50 volts and 100 volt. Each resistor is 30 ohm per volt. Okay, this is not a fixed resistor, but the resistor has a value that depends on the voltage. So 30 ohms per volt. So kalau you imagine this resistor is not like a normal resistor that you use, but actually you can adjust the resistor level. So usually we can adjust by using different lengths of wire, or we can use variable resistor. Okay, so now the material of the resistance used here, the characteristic is given as 30 ohm per volt. So we want to be able to measure 5 volt, 10 volt, 50 volt and 100 volt. And as the starting point, it has a potentiometer, and the potentiometer itself can measure 1.8 volts. Okay, so how we design? So we must start with R1 and then slowly increase R2 up to R5. This is the step. So R1, the voltage across R1 is given as 1.8 volts. The value of the resistance is 30 ohm per volt. So we multiply, the volt cancel out, we get the value of R1 is equal to 54 ohms. Okay, now we need to calculate what is the voltage across R2. So if we go back to the circuit, the voltage here is 1.8. The voltage here is 5 volts. So what is the voltage difference? Must be 5 minus 1.8. So we get the voltage across this resistor should be 3.2 volts. So that's why we have here 3.2 volts. We multiply by 30 ohms per volt. Again, the volt cancel, we only get ohms, and the answer should be 96 ohms. So now R2, we need to set to 96 ohms for us to be able to measure 5 volt. Now we repeat the process for R3. So R3, we want to measure up to 10 volts, but the previous resistance is 5 volts. So the voltage across here must be 5 volts. So similarly, the voltage across here must be 50 minus 10, 40 volts. And the voltage across here must be 100 minus 50, which is 50 volts. So to determine the value of the respective resistance, so for R3, we get 10 minus 5, so 5 volt. 5 multiplied by 30, we get 150 ohms. And then for R4, 50 minus 10, so 40, multiplied by the resistance per volt, we get 1200 ohms. And finally for R5, for 50 volts, we get 1.5 kilo ohms. So the value of the resistance here is the value that we must set in the volt box for us to be able to measure voltages between 0 to 100 volts. Okay, this is how we calibrate for volt box. Okay, so far I've shared with you 3 types of calibration. One is the slide wire potentiometer. The second one is the single range dial potentiometer, and the third one is the volt box. So it is 12:52. We have about 8 to 10 minutes left. So I'm going to cover about noise now. So noise, this one is entirely theoretical, and you are only required to have a understanding of the elements that can cause noise. Okay, kalau kita translate bahasa Melayu, noise ni adalah bunyi bising. Bukan bunyi, bising, kebisingan. Atau hingar. Another term, technical term that is used. Okay, noise here, we are not talking about audio noise. We are talking about signal noise, even though audio is actually a signal as well. But we are focusing on electrical type of noises. Okay, so noise is basically, the definition is an unwanted disturbance in an electrical signal which can distort or reduce the signal quality. So you can see the figure here. Without noise, we can see a smooth sinusoidal wave. But with the noise, you see that the signal is distorted. So when it's distorted, it can, if you are talking about communication, it can reduce the quality. You cannot, if you are, for example, you are talking in the using your mobile phones or using your WhatsApp, maybe the sound will become not clear or something like that. So this can come from many sources. So we are going to look at the theory of the sources. Basically, we can divide into two types, which is correlated and uncorrelated. So correlated is when the noise is present only when the signal is present. So it comes together with the signal. So we say it as correlated. That means one is caused by the other. So uncorrelated is when the noise is already there, whether the signal is there or not. Okay, that is the main difference between correlated and uncorrelated. For correlated, there are two types of noise. One is harmonic, another is intermodulation. And for uncorrelated, there are many types. And it can be further divided into external or internal. Let's look at the correlated first. So we are talking about harmonic and intermodulation. So what is harmonics? I think you guys have already learned it. If not in depth, you must have already covered part of it. So harmonic is when we have a multiple of the fundamental frequency. Kalau macam power system kita kan, our frequency is at 50 Hz. So multiples of 50, 50, 100, 150, 200, 250 and so on, that is what we call as harmonics. Okay, so harmonics are caused, harmonics can happen to voltage waveform and also current waveform, and it is caused by non-linear loads. Okay, non-linear load maknanya perubahan penggunaan elektrik dia, penggunaan current dia tak bergantung kepada konsep linear. The more you utilize, the more you use. No. Okay, like rectifiers, discharge lighting, saturated magnetic devices. So these are all non-linear loads. It does not follow the linear path of current usage. So it can produce harmonics. So odd harmonics is most concern. Why? Because even harmonics, second, fourth, usually they cancel out each other because it's even. Okay, so one positive, one negative, they cancel out. But for third, fifth, and seventh, and so on, odd number, so odd number, it can add up. Okay, so for example, okay, this is example, the third harmonics. And the effect of harmonics is usually overheating. Kalau kita tak jaga kita punya circuit ada harmonics, then we'll see overheating in the circuit which can cause further damage if untreated. Or another effect is overloading. Okay, this is a simple example of why harmonics is not favorable or dangerous. So katalah kita ada fundamental frequency. So fundamental frequency alone, we have a very nice waveform. But if we have a harmonic at the third level or the third harmonics, so katakanlah yang ini 50 Hz, 50 Hz that means in 1 second it has 50 cycle. So the third harmonic, that means 3 times 50, 150, that means in 1 second it has 150 cycle. So you can see something like the shape of the pink waveform here. So because it's in the same circuit, this wave can superimpose each other. And you get a combination waveform that is no longer nicely shaped like this, but distorted. This is what is causing the overheating or overloading. So if you have another harmonic, let's say fifth harmonics, so for example at 250 Hz, so you have even a faster waveform, smaller in voltage, or smaller in the magnitude but faster, now you have the waveform becomes even more distorted. Okay, so how do you avoid this? One of the ways is by using a filter circuit. Okay, which we will not cover here. And another effect is what we call intermodulation. So intermodulation happens when we have two or more signals in our circuit, and the signals is not at the same frequency, or even maybe from the same frequency, but it can affect each other differently. So let's say we have two signals, one at frequency 1 F1, one at another frequency F2. Okay, so when we have two different frequencies, we see that when the signals are inside the same circuit, the frequencies can affect each other. We can have a combination of the frequency, or a subtraction of the frequency, or a multiple of the frequency, which can generate further complication in our signal. So here are the examples of intermodulation. Intermodulation, that means the signal has some modulation. The modulation of one signal affects the modulation of the other signal, and it forms other types of signals that is not intended for the circuit. So katakanlah you ada dua frekuensi, F1 dengan F2. So these are the potential combination of frequencies that can exist in the system. Boleh jadi F2 tolak F1, boleh jadi 2 F1 tolak F2, 2 F2 tolak F1, and so on. So these are also elements that can affect and produce noise in your circuit. Okay, kita tak tengok macam mana cara nak solve benda ni, kita just tahu dia punya teori saja dulu. And then for uncorrelated, we can look at external and internal. So these are common sense. Kalau you tengok, memang you boleh terus dapat. External is generated outside the circuit. Internal is generated within the circuit. So external, we have atmospheric noise. We also call it as static electricity. Okay, the most common is when you hear sputtering or crackling. Kalau you dengar radio tu, kadang-kadang bila you tukar channel, you dengar itu, ataupun speaker. Speaker PA system tak ada orang guna pun ada kadang-kadang ada bunyi. Bila you on tu dia itu adalah static electricity caused by electrical disturbance in the atmosphere. And then extraterrestrial noise. Okay, yang ini berkaitan dengan angkasa lepas. Noise that comes from outside the Earth's atmosphere. Dia ada kaitan lah, kalau you nak tahu detail, dia ada kaitan dengan Einstein's theory of relativity tu. Macam mana dapat detect the noise. Okay. Ada cerita lah, tapi sebab faktor masa, I'm going to go straight to the next part. And then industrial noise is also known as man-made noise. Yang ini common sense lah juga. Any noise made by humans, whether through industry or through personal, because of personal, caused by personal usage of equipment and so on. So kita panggil dia sebagai man-made noise. Dan noise ni adalah more obvious in densely populated areas, urban areas kan, macam Kuala Lumpur, Bandar Melaka. That one man-made noise is more, so it may affect your reading more significant compared to rural areas. So we call it as industrial noise. So ini example dia, kalau dekat kilang, commutators, automobile emission systems, AC power generating equipment, semuanya ada kesan pada noise. Dan interference. So interference pun satu jenis juga. Di mana kalau kita, so tadi yang contoh radio tadi tak tepat kot. Yang contoh radio tadi tu lebih sesuai untuk interference. When we change frequencies, sometimes the signal interact at different frequency within the same bandwidth, ada different signals. So kadang-kadang sebab itu bila kita tukar channel, kadang-kadang bila kita ni tiba-tiba dengar channel radio lain. So we call it as interference because of the frequency. And then internal is caused by the device itself. Okay, transistor adalah satu elemen ataupun satu komponen, one of the component that can cause noise. Because transistor involves the movement of current as well, and it has electrons and holes. Because we have PNP or NPN, right? It involves the movement of charges. So transistor is basically a switch. So when it operates, it can have and generate some sort of noise. And it can be also combined with the thermal noise. Okay, so this is the transient time noise. So you boleh baca sedikit dia punya teori ni. It relates to the current and also relates to the frequency. And the thermal noise is also related to when we carry the current involves heat. So heat itself produces some sort of vibration that can add to the noise in the circuit. Alright, so habis kuliah kita untuk hari ini. Ada apa-apa soalan? Any questions? Okay, kalau ada boleh type ataupun boleh on you punya mic. Okay, Divan says no. Alright, good. So you study this material first. Okay, for your information, again, I would like to remind. Okay, thank you. Maybe next week there will be a quiz which will cover this topic. So make sure you study this topic a bit so you know how to answer. Okay, that's it from me. Thank you. So I'm going to stop the recording now.